I can see the week is getting longer and longer. Bueno, bom dia. Vocês estão acordados? No. We'll see what we can do about that. Okay. So today we're gonna continue our que si están despiertos. Today we're gonna continue our lectures on dark matter. So let's review what we've done so far. So we looked at the generic kind of dark matter problem and talked about how do we make a kind of ideal dark matter detector. Then we started talking about specific technologies, and we covered the two of the technologies that are in use, so noble liquid gas, noble liquids, and we talked about the cryogenic crystal detections. We saw some of the limits that we currently have, and we talked about the Dama signal for a little bit. So today we're going to talk about a couple more detection technologies, and then we're going to talk about the neutrino floor. So today we're going to spend some time talking about how do we calculate when neutrinos, especially since this is a dark matter school, how do neutrinos come into the picture for dark matter detection. Okay, so last time we talked about kind of the low mass dark matter region, and we discussed that there's a lot of different technologies that are being put together, a lot of new ideas that are still, a lot of them are still in R&D, some of them are experiments that are being built. A lot of the experiments that are that were originally made for higher mass dark matter have now started looking at how can they do lower mass dark matter limits or search for dark matter in this low mass region, and we showed some results from Lux, and we're going to continue that trend. So I'm going to just advertise a little bit about bubble chambers, since we're going to have a talk by Andrew right after this one. But this is a really nice technology. We talked about how do you discriminate between your signal and your background, when one way to do it is to make your if you're looking for nuclear recoils, make your detector insensitive to electron recoils. So if your detector just does not trigger when you have an electron, a photon going through it, then it doesn't become a background. And so Andrew's going to go over how that works on these bubble chambers, either today or tomorrow. I don't know. It's one of the talks, right? Today, great. And he'll show you the limits that you can get with this technology. One of the nice things that he's going to tell you about is that we talked about different types of interactions between dark matter and the standard model, and we tend to kind of generically look at spin-independent coupling as the first base, but we do not know how dark matter is going to end up interacting with with the standard model. So we talked about the effective field theory and all these operators, but spin-independent is a really good another good way for dark matter to possibly interact. And so Pico is, because of the target materials that they use and the spin, they're particularly, that's another one of their strong points. So I'll stop there and I'll let Andrew tell you about that. Now another technology that we haven't talked about is CCD technology. So you can take a CCD camera or that was originally made for putting on an astronomical telescope, and you can say, well, if a WIMP comes by and whacks into one of the atoms in the CCD, you're going to get a nuclear recoil. And the nuclear recoil is that nucleus is again going to plow through your crystal, and as it does that, it's going to release ionize a track and release a bunch of electrons. If you have a big field in that region, those electrons are going to drift, just like in the TPC kind of thing, but here you're talking about inside a piece of silicon. and if this is a CCD, then you can read out that signal. And the electrons will have some drift pattern, which will, if you have an event here, and as they drift, they're going to generate charge collection in some region. One of the nice things about CCDs is that you have a technology that already has, megapixels in a detector, and so when you get something like this, you would get an event that actually is registered in more than 1 pixel, and the size of that signal can give you some information about the Z position. So there will be 3 different talks by Juan Estrada on this type of ideas, so I won't talk about it much more. And again, they are projecting very good. This is a projection of what they'll be able to do with a 1 kilogram year exposure of this technology. So I'll let Juan talk about that. And tomorrow we will talk about other types of dark matter searches. We'll talk about hidden photons, and that's another region where this type of technology is very interesting. Okay, so I won't say anything more about those 2, but those are 2 interesting ones that you'll hear more about in the next 2 or 3 days. So the other idea that I'm going to talk a little bit more about that we've already introduced is the directional detection. So as we said before, the galaxy is rotating, and the sun is rotating with the galaxy in the disk, and so we're plowing through the dark matter halo, and so from our point of view, right, we see a dark matter wind coming at us from the direction of Cygnus. That's just a generic direction of the constellation Cygnus, which is where the sun is headed toward. And if you have the planet and the planet is going around, at some part of the day the wind is going to look like it's coming from the ceiling, and another part of the day it's going to look like it's coming from one of the walls. And so if you can tell that difference, then you would be able to get a very good signal, which is very hard to do with any other background. And you would get a signal that looks something like this. So you'd get some dipole. So this is a projection of the sky, and you're going to get some directionality. You're going to see that you get a preferential direction pointing towards Cygnus, and that's a very good. That would be a very good signal. Now, as we talked about, the hard part here is getting the mass, right? So I'm going to just give you 2 quick slides. This is just taken from review talk that was in a conference called IDM. I was like a week or 2 ago, last week. So I very blatantly stole 2 slides from them, so I can show you kind of the overall picture. So there are a couple of technologies that are looking at different ways of doing directionality. So there are different ideas. Some are using emulsions. So this is basically kind of like a old style camera that had film, and the film will show you a track, and if you have a recoil on the track, you will be able to see that track. And so by having a bunch of these emulsions, you can kind of expose them to dark matter. You can kind of rotate it around so it's always pointing toward the wind, and then you can look for tracks that are aligned with the direction of the dark matter if you align these guys so that the dark matter is going through it. Their idea is to use carbon nanotubes to basically generate some charge and generate a signal. As we had mentioned, there are people that are looking at different ways of using either crystals or directional information that has to do with a crystal or a solid that would basically change the cross section. Sometimes people are trying to get the direction inside of a solid, or you can say maybe the rate will change if I have a different cross-section that depends on the crystal orientation with respect to the wind direction. So there's a couple of papers out there. And then there's this idea of using graphene that's called Ptolemy G3, where you have the graphene sheets that would basically generate electrons that you would see if you have a bunch of layers of this stuff, and you can kind of make a tracker basically for the dark matter signal that would depend on the direction. So these are all kind of more exotic new ideas that are in R&D. For directional detection, most of the effort has been in using a gas, because of course the gas will allow the nucleus to move further. And so it's basically just like the bubble chambers we talked about before. You would have some wind of WIMPs, and you would hit a nucleus, and then there'll be some field. That nucleus is going to generate a track of electrons. Those electrons are going to drift, and then you collect that drift, those drifted electrons at with some form of charge readout that will allow you to reconstruct the track in some three-dimensional form. And so there are different ways to do that, whether you do it with something that scintillates and you get some position. Most of the ideas will have a some form of readout where you drift and then you collect the charge at one of the walls. So we have drift, which is one of the first experiments to be using this idea. They've been running an experiment for a long time. They have about 1 meter cubed of volume. And then there's a couple of other ones that are using different technologies to kind of do the same thing in different, slightly different ways. So there's groups using micromegas, and these guys are New Age is another type of technology that's again using charge readout, and then these guys are a new type of readout using these chips from Atlas. But they're basically all using the same idea of we have a track, we're going to drift something, and we're going to try to recreate that track. So this is hard to compete. So the directional detection technologies have a hard time competing with something like noble liquid or our bubble chamber, or even with our crystal detectors, just because when you have a dense liquid or a solid, you just have a lot more atoms. So if you have a volume of detector, you have a lot more target. And as we talked about, target, exposure, target times time is one of the ingredients you need for dark matter detection. However, if you can imagine, we find dark matter, let's say in the next 2 years, the next results from xenon 1 ton or one of these low mass technologies sees a signal and it's confirmed to be dark matter, then we are looking at the next 20 years trying to understand dark matter and making measurements that are going to go from that discovery to the actual physics of what dark matter is. And so I think directional detection might not necessarily be the technology you would use to discover dark matter, but I think that it is not unreasonable to think that if dark matter is discovered soon and it's in the right, cross-section mass range for some of these technologies, you can imagine a second or third generation experiment that would use some type of technology to actually do this directional measurement. Does that make sense? So I think it's still it's a good idea. It's very hard to pull it off. But if we do find dark matter, then there'll be a lot more money for doing bigger experiments, and maybe this will become something that we can do kind of as a post-discovery measurement. Okay, so reviewing all of these things, we have CCDs, we have bubble chambers, and you're going to hear a lot more about those two. And then we have directional detectors. There are other ideas. If you look at people are continuously looking for different ways of doing things. There's a really interesting idea that uses DNA strands to look for dark matter. So there are people looking at other, just using other technologies that have been either used in chemistry or biology. There are techniques that are established that were developed for something else, and they're trying to say, well, can we use this as a dark matter detector? So there's a lot of new ideas floating around. All of those are kind of in the R&D stage. Okay, well, that was interesting. Let me go back. Okay. There we go. All right. So now we're going to spend the rest of the time today talking about the neutrino background. So we have dark matter detectors. We're trying to find dark matter. And one of the speakers mentioned that, we were doing this calculation of how many dark matter particles are going through my hand in this room right now. And it was something like 20 million dark matter particles going through my hand in this room right now. However, there's way more orders of magnitude more neutrinos going through my hand right now. And so you have to ask yourself, if you have a detector that's very sensitive, would we be able to see these neutrinos instead of the dark matter, and when does that happen? So we can look at neutrino interactions and say, at low energies, we have these elastic and quasi-elastic processes. You guys saw this already, so I'm not going to belabor it. I guess the only thing I'll say is that this neutral current is very interesting, because the neutral current, where you have a neutrino bouncing off the nucleus of an atom, looks a lot like a WIMP interaction, right? So this is basically the same diagram, except that instead of a WIMP particle or a dark matter particle, I'm putting a neutrino here. So this is definitely something that would generate a signal that's very similar to what you would expect for dark matter. But all of these guys can become backgrounds. So one thing we can do is look at the cross sections of these processes. So if you look at the cross sections, this is what you get. And you can see that that neutral current one is called coherent elastic neutrino nucleus scattering. Is not one that you see very often talked about, because it's not one that detectors normally are sensitive to, because it's very low energy and it's the whole nucleus, but it is the highest cross section. And depending on the neutrino energy, you're going to be dominated by this interaction, except that the actual energy deposited in your target is very small. So for most neutrino detectors, they don't care, because they can't see that. Except that, of course, one of the other things that we were talking about you need for a dark matter detector is a very low threshold, right? Because dark matter is not going to give you a lot of energy when it hits your detector. So for dark matter detectors, this definitely is something that we have to pay attention to. All right, so what cross sections are one thing. So that gives you kind of the relative rate that you would expect. The next thing that you will have to talk about is, well, what actual neutrinos are going to be going through your detector. So we can look at different sources of neutrinos. So, just sitting in this room, right, we have neutrinos that are coming from the sun, that are coming through this room right now. There are neutrinos from diffuse supernova background. So basically all the supernovas that have gone on in the past in the galaxy, every time a supernova goes on, it releases a bunch of neutrinos, and that just creates basically a diffuse flux of higher energy neutrinos that are roaming around the galaxy, and some of those are going through this room at any given time. Then there's the atmospheric neutrinos from cosmic rays. So you have all these protons and other particles in the cosmic ray flux that whack into the atmosphere. They generate muons and they generate neutrinos, and so those neutrinos are going through our through the room. Then there's the neutrinos from the core of the Earth. So you have heat in the Earth, and you have processes that generate neutrinos. Those neutrinos are coming up from the Earth toward us. There's probably some nuclear reactor close to Sao Paulo somewhere. I have no idea, but there are reactors, and those reactors are generating neutrinos, and if you're close enough to one, you'll see those too. And then there are neutrinos from your own detector. So you can have a detector that has some radioactive decay that produces a neutrino. And so depending on the process, you might actually see your own detector's neutrinos. And then there are supernova, which happen in a burst, so they're not really a background, it's more like a signal, but it's another thing that a dark matter detector might be able to see. Right? If you have a close by supernova, is going to generate a burst of neutrinos, and a big enough dark matter detector might see those. Okay, so you already saw this slide from the sun. So we have all of these different flavors of things that make neutrinos. And I'm not going to go through the whole process, but basically we can list all of the PP neutrino chain in the sun and say, okay, here are all the neutrino species that we will see, that we expect, and we can then plot those to see what their energies look like. The diffuse supernova background, basically you can try to figure out, well, as a function of distance from us, what's the rate of neutrino interactions, the rate of supernova that are going to generate these neutrinos. And of course, if you're close, you're not going to have a lot of supernovas that are close by because those are rare events. But as you move further and further out, then the volume increases. So the number of potential stars that are at the end of their life cycle that are about to go supernova increases. So you'll see an increase in the number of supernova as you move out in redshift. And those all then make this diffuse background that's coming at us. Then there's the atmospheric neutrinos, which come from different types of processes. So, muons and pions decaying and kaons decaying. And so they form all sorts of different neutrinos. And you can then write down, okay, I'll have, that fraction of the neutrinos from atmospheric interactions are going to be of this particular type. So we can list those as well. We can look at the geoneutrinos and look at their spectrum. So there's different decay chains in the Earth. So you get all this neutrinos being generated from just the rock and the trace elements that we have there. And so those generate some neutrino flux, which as you can see is pretty small in energy. So this is kind of in the 1 to 2 MeV range. So you take all of those things and you can put them together, and you can make a plot that shows what the neutrino flux versus energy looks like. And you'll get something that looks like this. And I think, in this plot, I have not included the geoneutrinos because the geoneutrinos, the flux is orders of magnitude lower. So at no energy range that we're interested in, the geoneutrinos dominate. So I mentioned it for completeness, but we're going to ignore the geoneutrinos because the solar neutrinos at those energies of 1 to 2 MeV are much higher flux. And so this is basically what you get. So this is a bunch of high flux from the sun. So these are all the neutrinos coming from the sun. And some of them are lines, depending on that solar table. Some of them are 2-body processes, some of them are 3-body processes. So you get either a line or some distribution. And you can kind of plot those like this. And then you have the atmospheric neutrinos that look something like that. And they go to very high energies. And you have the diffuse supernova neutrinos here, which are kind of in the middle, and they only dominate over a small energy range here. But they do contribute to your overall spectrum. So now you have all of these neutrino sources, and you can ask, okay, how do I look at that from a point of view of a dark matter detector? So as we talked about, the highest cross-section is this 7's coherent elastic neutrino nucleus scattering, which is very similar to the dark matter interaction. So in dark matter, you have this A squared term, right? And we talked about the spin-independent coherent interaction. And you have a same type of process with neutrinos. So this is going to be our dominant interaction for a dark matter detector, something that will make a signal that looks like dark matter. So if you get a dark matter detector that is sensitive enough, we'll be able to see this interaction. So we can look at how much energy you expect from different energies of neutrinos. So this is the cross-section for sevens, for the coherent elastic neutrino nucleus scattering, as a function of recoil energy in your target. And this is for xenon, germanium, and argon. So the different colors are different targets, but you can see that they're mostly similar. And then as you change the energy, so 7 MeV is going to, a 7 MeV neutrino is going to give you around 1 kV or lower recoils. And a 40 MeV is going to give you kind of 100 kV, and a 200 MeV is going to get up here. So you kind of see that we're looking at the right range of recoil energies where we're actually looking for dark matter. So this is important. If I take the spectrum of neutrinos that we showed you before, and I convolve it with this cross-section, I can then show you the recoil energy each of those different neutrino lines generates in a dark matter detector. Okay? So that's what this plot is. So this plot is the, and I'm sorry, this is kind of going on the corner of the projector. This is the event rate in ton years per kV. And what I've done is basically shown every single one of those sources that we looked at before. The first plot was the flux. This is the recoil energy that you get in a target. So in my dark matter detector, if I have a particular neutrino species, like this is the PP neutrinos, they're going to give me recoil energies that are, you know, this is around a couple of EV. So I'm probably not going to be too worried about PP neutrinos from the coherent elastic neutrino nucleus scattering. Although they're the highest flux, they're giving me EV size recoil, so unless I have a detector that has a threshold below that, I don't have to worry about them. Does that make sense? So every detector that you have, you can say, okay, if my detector can only see 1 kV and higher, then I can ignore all of this stuff. But look at this guy. This guy is the boron 8 neutrino signal. So this little purple guy here is boron 8. And the black line is the signal from a WIMP of a mass of 6 GeV with a cross-section of around 10 to the minus 45, which is a perfectly good dark matter candidate that has not been ruled out. And if your detector has a threshold that looks that gives you a kind of a window that only looks like this. Whoops, sorry. There we go. So if your threshold is around here and you don't have enough exposure to see down here, this is all you're going to see. And if that's all you're going to see and you see the signal, you might say, hey, I'm looking at a dark matter signal, right? Because they look exactly the same. And so that is the trick that we're going to look at, is to say, well, you could interpret some of these neutrino signals as a dark matter signal if you're only looking at a particular size of a window. And you would be seeing the signal from neutrinos. If you didn't know that solar neutrinos existed, you would say, aha, I'm looking at a dark matter signal. I'm going to find out what dark matter in cross-section that corresponds to. Right? And I already told you that that's a mass of 6 GeV and a cross-section of 10 to the minus 45, but that is dependent on my target. So if I change my target, I'm going to reconstruct that neutrino signal as a different type of dark matter. So this is one way I could see that if I didn't know that solar neutrinos existed, and I was seeing the signal, this is one way I could see that this was not dark matter, because I would take my target and I would reconstruct what I thought that dark matter particle was, and depending on the atom in my target, I would get a different mass for that, and a different cross-section as well for that for that reconstructed quote-unquote WIMP. But maybe you are not looking for spin-dependent dark matter. Maybe you're saying, oh, I think maybe when I'm looking at a spin-independent, instead of a spin-independent, I'm looking at a spin-dependent dark matter particle. So if you interpreted your signal as spin-dependent dark matter and you tried to reconstruct it, then you would get a very different cross-section. So these are all the points we were looking at before. Although they are slightly different in cross-section, they're all about the same when you're looking at the spin-independent case. But for spin-dependent, you see that depending on the type of interaction that you're assuming, you're going to reconstruct very different cross-sections. So we can do this exercise for many different types, and so I can say, okay, here are all of my types of neutrino interactions, and I can reconstruct where in the cross-section WIMP mass plane I would think those are if I interpreted them as WIMP signals. And I will get this bunch of different points for all of these different guys because they have different spectra. And you see these start to spread out for the atmospheric neutrinos. And you guys remember we talked about this, I think yesterday or the day before, that it's hard to reconstruct the mass when you get to very high recoil energies because of these form factor nuclear, the fact that when you get enough energy, the particle doesn't see the entire nucleus, it starts to see the independent pieces of the nucleus, and so this coherence starts to break down, and that gives you some broadening of the reconstruction of the mass, and so for after a particular mass, it gets very hard to actually pin down the mass, and you basically end up with these long tracks of reconstructed potential mass for your WIMP. Now, these are not actually fair because I am fitting a particular dark matter, a particular neutrino species with a WIMP model, without taking into account that when I have neutrinos from the sun, I don't only get PP neutrinos, I don't only get boron-8 neutrinos, I get all of them. So I have a spectrum that does not look exactly like a WIMP spectrum, it has all of these humps in it. So in reality, what I need to do is take them all together, and then I can say, okay, well, if this is my overall spectrum of neutrinos that I would get in my detector, and I think they are dark matter, and I'm trying to fit them, what would I fit? And what I get is something like this, where depending on my threshold, if I only see from here up, let's say that my threshold is 20 keV, then this would look at a very nice dark matter signal, because I'm not seeing this big hump. So all I see is this part. Does that make sense? Now, if I'm looking at the boron-8 hump, which is right here, and my detector doesn't have enough mass to see this guy, then I'm only seeing this. That also looks like a very nice dark matter signal. But if I have a threshold that starts to see these humps, and I try to fit the entire thing with a dark matter profile, it won't be a good fit, because dark matter doesn't have these humps. Right? So depending on my threshold, I'll be able to distinguish the neutrino signal better from the dark matter signal because I have all of the structure inherent in all of these species of neutrinos. And so what we're going to do is take this idea and then map it on to the so-called, to the cross-section mass plane and make this plot that was done in this paper by my group a couple of years ago. It's been worked out by other people. This particular one is from this paper. And so we're going to talk about what this means. So what is this so-called neutrino floor? And in our paper, we never called it the neutrino floor. We called it a WIMP discovery limit. So let me talk about what that is. So the point is we're trying to figure out where in this mass plane do you start to have problems because you are starting to have neutrinos become a background for you. And so we basically define this WIMP discovery limit as the point in which if there were a WIMP model that lies above that limit, then a given experiment has a 90% probability to obtain a 3 sigma detection of the signal. So let me break that down. So you have a neutrino signal, and your detector's taking data, and you're seeing the neutrino signal. But let's say that dark matter is also there, and the cross-section is a little bit above the rate from dark matter is enough that you can tell that you're getting more signal than you would expect from just the neutrinos. So I'm going to say, well, I need to be able to differentiate my dark matter signal from my neutrino signal to some statistical level. And so I'm going to call that 3 sigma. And I'm going to do one experiment, and one experiment has some statistics. And so in one experiment, I might get 2.5 sigma. In another experiment, I do run the same exact detector again. I take data again, but again, I get statistical fluctuations. This time, I get 1 sigma. And some other time, I get 4 sigma, right? And so if I do many experiments, if 90% of the time I get above 90%, above 3 sigma 90% of the time, I can say, okay, that is a dark matter signal that I would be able to distinguish from neutrinos. If 90% of the time I only get a 1 sigma excess, I'm not going to be able to say I'm really seeing a dark matter signal. Does that make sense? So that's my WIMP discovery limit. It is the point at which I'm going to reliably be able to see an excess over what I expect, to the point where I would say I see a 3 sigma excess over my expected neutrino signal. And that's what the WIMP discovery limit is. So to calculate that, we construct a likelihood function. That's this complicated thing. And we're not going to go into the statistics of it, but I'll just tell you what these, I'll point out what these things are, and we can discuss that off topic or off lecture. So basically I have some likelihood of a particular WIMP model and cross section for a given neutrino flux that will depend on the number of WIMP events that I see, the number of neutrino events that I see, the distribution of my WIMP recoil, so what that recoil distribution looks like, and the neutrino recoil distribution, so I have to differentiate between those two, and then I also account for the uncertainty in the neutrino flux. So there was a point that I think Stefan was making in one of the previous lectures about if you had, for example, for the positron, if you were looking for the positron and you saw one event, you would be able to say, I discovered a positron, right? Because this event had no background, like there was nothing else that could make that event. This is not this case, right? Because if I knew what the neutrino background was exactly, then if I saw one event above that neutrino background, I'd be able to say, I'm looking at something else that's not neutrinos. But we don't know the neutrino flux exactly. There are some statistical and the word is escaping me right now. So there are some variations in our knowledge of that flux, right? And so we have to account for that, and that's what that last term is some uncertainty in that distribution that can come from your experiment or from the known values of these fluxes. So we use this likelihood ratio test to determine what cross-section here would get me a 3 sigma detection or higher 90% of the time. And that cross-section for each mass becomes my neutrino floor. Does that make sense? Maybe? Half and half? All right. Now, it turns out that this all depends, as we're talking about, the uncertainty on the neutrino flux, right? If I knew the neutrino flux exactly, I would always be able to tell the difference between an experiment that saw only neutrinos and an experiment that saw neutrinos plus something else. You follow that? So in reality, there's no such thing as the neutrino floor. Because if I keep taking data, if I take more and more and more and more and more exposure, my statistical uncertainties in the measurement of the neutrinos keep going down, and I would be able to see a increase over that statistical uncertainty. Not only that, there's some, basic, there's some given uncertainties on the actual flux that I can't get over, but as we were talking about, the shape of the neutrino fluxes is different than the shape of the dark matter. So if I keep taking more and more and more data, even if it's a tiny difference, my statistical test is going to start to see that tiny difference. And so I'll be able to start saying, wait a minute, this looks more like the neutrino flux than it does the dark matter flux, right? If I have an infinite exposure, I would be able to see that difference exactly, and there would be zero uncertainty between the neutrinos and the dark matter. Does that make sense? And so formally there's no neutrino floor, because if I keep getting the exposure up, I can basically distinguish better and better between dark matter and neutrinos. And you see these peaks here. This peak is at the boron 8, because as we were talking about, that boron 8 hump looks a lot like dark matter, so it's harder to distinguish it. But if I keep increasing my exposure, I will still be able to, at the corners, see the differences between the two spectra and differentiate them. So the neutrino floor is not an actual floor, but it is a practical floor, because this is a freaking ginormous number. Right? Like, we're never going to have 10 to the 6 ton-year exposures. And Andrew I don't know if Andrew's contemplating a 10 to the 6 ton-year. There isn't enough xenon in the planet to make an experiment that'll give us a 10 to the 6 ton-year exposure. I think. We can calculate that later. But, this is, so practically, there's a point where you just can't get an exposure that big. And so for a practical experiment, you will have some maximum exposure that you expect to be able to get, and that will give you some WIMP discovery limit that you will hit. Does that make sense? So we can look at how that works for this boron 8 region. So if I only look at the boron 8, and I'm concentrating on that, I can make a plot that, let's think about what we expect. So if we are looking at a dark matter signal that's really strong, right, much higher than the neutrino level, my experiment is going to see dark matter, and the neutrino flux is going to be so low that I'm going to get, in my exposure, let's say I'm going to get 0.01 counts from neutrinos in that exposure, but I'm going to get 100 counts from dark matter. In that case, as I am continuing my exposure, if I double my exposure, I get 200 events from dark matter and 0.002 events from neutrinos, right? So in that regime where I'm dominated by dark matter, my sensitivity is going to go as MT, as my exposure, as the mass times the time. It's going to go linearly because I'm in a zero background regime. Does that make sense? Now, if I start seeing neutrinos and I have to statistically subtract the neutrinos from my signal, then it's going to go as what? What do you get? How does the sensitivity go with exposure when you're subtracting a background? The square root of the exposure, right? So once you're subtracting statistically a background, your sensitivity goes as the square root of the exposure. So we expect that we're going to see a region where things are going as linearly with exposure. When you start kind of seeing neutrinos, you're going to go as the square root of the exposure. And then when you start digging in underneath the neutrino flux, when you're dominated by the neutrino, that square root exposure will break down. And that's exactly what you see. So this is a plot of the discovery limit. So each of these dots is basically this point for the boron 8 as a function of the here I'm instead of exposure, I'm plotting it as the number of neutrino events, because that's a better, right? The exposure depends on the experiment and all this kind of stuff, but basically you're going to have an experiment with a particular exposure, and you're going to expect some number of boron 8 neutrinos. So as that number is a fraction, so expect basically no neutrinos in your experiment, and these lines are just to guide your eye, the WIMP discovery limit goes roughly as linearly with exposure. And then when you get to somewhere around a fraction to 1, then it flattens out to a square root. And then you get to a point when the uncertainty in your neutrino flux starts to dominate. And so you get to a flattening out. So this is the saturation regime, where essentially, if I know that my expected flux is between here and here, and I see a signal there, I don't know if that is neutrinos plus dark matter, or if that's neutrinos only, because my uncertainty in my flux of neutrinos is between here and here. So I can't tell. Right? So as I keep going in my exposure, I don't get any more sensitivity to the dark matter flux, because I'm stuck just from that uncertainty. Now, if you keep increasing the exposure, then you start to see the little tweaks in the shape, and the little tweaks in the shape starts to become statistically significant, and then you are able to tell the difference. So if you keep increasing the number of neutrinos, your spectrum gets better and better, and you kind of get over the hump and start going as 1 over the square root of MT again. And how long you spend on that flattening saturation regime depends on how big your uncertainty is, right? If my uncertainty is really small, I only need a little bit more exposure to be able to tell the difference. If I have a really big uncertainty, I'm going to have to get a lot more events before I can start seeing the differences in the shape. Right? So that's why this, for a bigger uncertainty of 20%, you have a big flat part, and for a very small uncertainty, it basically takes a lot longer to reach that kind of saturation regime. Okay. And just for reference, that's kind of the Super CDMS Snow Lab exposure that we're expecting. So we're kind of trying to get to the place where we are starting to saturate. And so you can define a neutrino floor based on a kind of logical exposure of what a next generation experiment is going to do. We can then look at this region of atmospheric neutrinos, which is more where the more relevant for the higher mass, kind of 100, 200 GeV WIMPs, and we can do the same thing. So if I pick a mass and I plot that, I get a very similar curve. And so this is exactly the same thing, but now for higher mass dark matter. And I can plot where LZ is going to be, or where a next generation experiment is going to be. And if you're like really ambitious and are thinking about a gajillion kiloton xenon experiment, you could even imagine a G4 line somewhere out there, right? Somewhere over here. But you can see the problem is that after LZ is not exactly in the place where it will gain a lot, but the next generation guy is going to be squarely in this flat part. So making an experiment that's 10 times bigger than a 10 times bigger LZ experiment won't actually give you a lot more sensitivity to dark matter. And that's why we call it the neutrino floor. Practically, if you can make an experiment that goes all the way out here, it wouldn't be a floor, but this is, a couple of orders of magnitude bigger experiment than LZ. And so practically, you can see that, from LZ, we have one generation or two at max to go before we're just going to be in that neutrino floor, and making bigger experiments won't yield more WIMP sensitivity. So we can again define some neutrino floor based on something like that. So we can kind of pick which of these exposures we would expect for these experiments. So we can call these two curves kind of what the G2 and G3, generation 2 and generation 3 high mass experiments would be at. And we can do the same thing for kind of the generation 2 and generation 3 low mass experiments. And so what we've done when we've put together this neutrino floor curve is to pick exposures that are more than what people are planning to do now, with thresholds that are better than what people are planning to do, but not crazily bigger, right? So that it's a realistic place where you say this is going to be difficult beyond this point. And so we've picked, we've picked these thresholds and exposures, and we kind of stitched together a region for the solar neutrinos, and we stitched together a region for the high mass, and then you put those together, and that looks something like this. And those are target dependent, so depending on your target, you're going to get a different curve. Okay? For targets that are for like bubble chambers, and targets that are that have multiple elements, then you get more structure in that neutrino floor, because different atoms in your target react differently to the neutrinos. And you also have to take into account whether you are a energy resolving or non-energy resolving experiment. And as Andrew will talk about with bubble chambers, you can't you don't know what the energy of each event is, and so these guys, like the C3F8 gets flat here because you're assuming that you don't have energy information. If you did have energy information, then it would look more like this other pinkish line down here. So you can do, and I've put some of the other experiments there. I think I'll just skip that. All right, I'm running a little bit short on time, so I'm going to go over this last part very quickly. So that's the biggest neutrino background, is this coherent scattering. But you also have other effects. You have all these electron scattering cross sections. Now, when you look at the cross sections, those are 10,000 times smaller than the coherent scattering. So why would those be important? Well, if you have an experiment that's big enough and it has beta emitters or other reasons, you might get enough of these events that they actually become a background. And so for xenon, this is a plot of the event rate, and you can see that you get this this event rate from the double beta decay isotope of xenon 136. That looks like that, and then you have the PP neutrinos from the sun. Now PP neutrinos for coherent scattering give you a very small recoil energy, but if it's electron scattering, the electron has a lot smaller mass, so the electron in your target is going to get a lot more energy. And so the PP neutrinos actually are the dominant background from neutrino signals in the electronic regime, not in the neutral current regime, right? So you get this big hump of PP neutrinos, and then this plots different dark matter signals to see to get an idea of how that looks like. Now this line is not a line of the PP neutrino flux. That's the line, that's the residual line, assuming that you can reject 99.5% of all electron recoils. Remember that when we talked about liquid noble gases, you get a different S1 to S2 ratio when you have a electron recoil than you have a nuclear recoil. And so you can have a window in which you're only looking at nuclear recoils. But only is not an actual term, right? Because there's a distribution, and there's a tail to those distributions. So there's a tail from electron scattering that goes into your nuclear region, your nuclear recoil region of your experiment, where you're looking at that signal. You still have a tail from the electron recoils that bleeds in there. And so if you can reject 99.5% of all electron recoils, this line is what's left over. So you can see that if you weren't able to reject electron recoils, this line would be 100 times bigger, right? And so you'd be in really deep doo-doo in that case. But here, you still have to worry about it. All right, so you can add all of these contributions. So this is a paper, not by me, that adds both the contributions from coherent scattering and electron scattering, and basically gives you an overall background from neutrinos that you'll see in these noble liquid experiments. And so the bottom line is that when you do all this and you compare the sensitivity, when you add, so this is a comparison with exposure, and you say, well, what's my sensitivity if I only think about the coherent scattering, or I add all of these electron scattering backgrounds? The answer is that it does affect you, but not by orders of magnitude. So as long as you can reject, because these technologies have the ability to reject electrons, and the spectra are different, have different shapes, you still have the ability to distinguish a dark matter signal from these backgrounds, and it does affect your sensitivity, but not by that much. All right. So the last thing I'm going to talk about is, can you get beyond the neutrino floor? So how do you get beyond that? And one idea is to say, well, we already showed that you can reconstruct these neutrino signals as dark matter, and when you do that, it's a target-dependent reconstruction. So maybe if I use different targets, I'll be able to tell the difference. So I'll go through this quickly, because I'm running out of time. So when you do that, you find that for the spin-independent case, it doesn't really help that much. So these are WIMP discovery limits where you've added a xenon experiment, and then you say, oh, okay, well, what if I have a xenon experiment and a germanium experiment, and a germanium experiment, xenon plus silicon, and you keep adding different targets? You can see that that you don't gain a lot in your WIMP discovery limit. So your neutrino floor basically doesn't, that's not a strategy that will really work that well. For spin dependent, however, you do gain a good amount if you start adding different targets, and that makes sense because you saw that the reconstruction for spin dependent was a lot bigger. There's a lot more scatter, so you can tell the difference more. So when you start adding different targets and looking at all the data together, you can lower the you can go at least lower what the effective WIMP discovery limit is. And then the final thing is, again, talking about directional detection, you can say, well, what if you had directional detection detector? Could you go beyond the neutrino floor with a directional detection detector? Again, this is very hard to do in practice because, again, you would need a ginormous directional detection detector, but from a formal point of view, could you do it? And the answer is absolutely yes. So this is a plot of the attitude and azimuth in the sky, and this is the position of the sun at different times, and this is the position of the direction of the WIMP wind for those or the inverse of it. So where would the WIMP be coming from, and where would the sun be? So if you could tell the direction of your recoils, all of the neutrino events are going to be coming from there, and the dark matter is going to be coming from here. So one question is, do they ever meet? And the answer is they actually they don't, especially for higher recoil energies. You can see that this is the minimum separation and the maximum separation, and this is for different energy bands. So at this higher energy band of 3 to 5 keV, these two things never meet. So you would be able to distinguish a solar neutrino signal from a dark matter neutrino signal. So in principle, if I can make a directional detector that is sensitive to these energies, and that is big enough to actually see these signals, I would be able to distinguish between the neutrinos and the sun, and that theoretical detector would not see a neutrino floor, because you would always be able to see the difference in direction. So in that particular case, when you have a directional detector, you always go down as MT. Actually, that should be, yeah, MT, because you're killing your background. All right, I think I will stop there.
We set up for the next speaker. We can take a couple of questions. Questions?
Not all at once, please.
How much does it change if you include atmospheric neutrinos in that study?
Okay, can you repeat the question? How much does it change?
In the directional detection, if you include atmospheric neutrinos.
Ah, yes, that's a good point. So the plot that's a really good question. The plot that I was showing you was for solar neutrinos. For atmospheric neutrinos, it is less sensitive, and it's also a lot harder because, as you saw, the neutrino floor is already very low. So to get a directional detector that would have sensitivity down to 10 to the minus 50 centimeters squared, it would have to be a really big directional detector. And the atmospheric neutrinos are coming from all over the place. And so what would happen there is that you would be able to cut a fraction of the atmospheric neutrinos and model that, so you would be able to subtract it out. So in that case, your exposure would go as the square root of MT and not saturate. Whereas here, since you can totally kill the signal because they're in different directions, for this case, your sensitivity goes as MT. But practically, it's really hard to imagine a directional detector that big, although again, it's not impossible.
About the directional detection, how does the detectors you showed us get the information about the direction? It was not so clear. I think I was sleeping. I don't know.
Yeah, so it's exactly the same thing as the bubble chamber TPC. You have a track, you generate a bunch of electrons, you drift those electrons into a plane that gives you an XY picture, and you get the time it takes for the electrons to come down, and that gives you a Z coordinate. And usually you have some other trigger that'll give you that initial time. So it can be scintillation, people are using different techniques. But if you get a T0, it's basically the same idea as a TPC. You need an S1 to give you a starting time, then you measure a drift time, and then you get an XY position from the collection of the charges, and you can reconstruct that 3D track. Other technologies or studies have shown that just having a 2D track without the three-dimensional information is still very good. So statistically, you can still make a directional detector that just gives you the XY position and does not know Z, and it's still a good discriminator for dark matter.
But we only get the, like if you think about collision, we only get the final state. The initial state could be anything for dark matter. Oh, no.
Yes, but the point is that the direction, so this is a statistical measurement, right? Like, you don't know which direction the dark matter came from. You're only seeing the recoil, but statistically, the recoils are going to be pointed in the direction that the dark matter was coming. You know, some are going to be like this, some are going to be like that, but statistically, there's a cone, you know, there's some angular distribution that'll tell you where all of these events are. So you can't do it per event, But you need, if you have 100 events, that's enough to give you a direction.